According to normative data, O2 consumption levels should stay roughly the same during steady state exercise. Both Summer and Josh's data suggest that this is correct, as their data differs slightly by 1 or 2, but stays within the range throughout the whole test. Max's data is different in contrast, as we see dramatic decreases and increases. This may be due to experimental methods, as it is unlikely that his O2 saturation would range this widely. This data may be disregarded because of this. Next one is breathing rate. All Josh Summer and Max's breathing rate started at different values at 2 minutes of exercise. The chart then shows that all three people's breathing rates had an initial increase between 2 and 4 minutes, and then showed a plateau between 6 and 18 minutes, where it then showed a decrease in breathing rate from 40 to 30 for Max and 30 to 20 for Summer and Max. As we see, Max's breathing rate is much higher than the other two's data. This is due to a technical error on the heart rate monitor used on him, where when he was participating in the test, it showed a lower reading than was correct. The normative data shows that there is a slight increase in breathing rate, and there is a plateau and a slight decrease once exercise is finished. In comparison, all three participants followed these trends. Although Max's heart rate was much higher than the others, it still followed the trend. My next one was diastolic. My next one was blood pressure. So I had two. I had diastolic blood pressure and systolic blood pressure. The diastolic and systolic results were taken from Max and Summer differentiated quite a lot throughout the test. As we can see, Max's diastolic blood pressure was at 78 at 2 minutes and dropped to 44 at 4 minutes, meaning there is a decrease, whereas according to Mark Adams et al. 2010, diastolic values should stay the same or decrease slightly, whereas Max's has decreased by 34 in 2 minutes. This is a trend in Max's data, and this may be due to experimental method and faulty equipment. This contrasted with Summer's data, as we can see her diastolic blood pressure stays relatively between 80 and 60 from 8 to 20 minutes, which is what is suggested should happen. As we can see, Max's and Summer's systolic blood pressure results were quite different too, as Max showed a varied amount of values, whereas Summer followed a normative trend of increased systolic blood pressure. Summer shows a steady increase from 4 to 6 minutes, where she most likely became fatigued and had a drop off at 20 minutes, whereas Max's data had a dramatic spike at 8 minutes, which went from 120 at 6 minutes to 215 at 8 minutes. This may be due to experimental method and may be disregarded, as it seems like this data is not correct. My next one was Borg rating. So as we can see, Max's, Summer's and Josh's results show varied values. Max and Summer both showed an increase when asked about the Borg rating during the test. And as we can see, from 4 to 8 minutes, both of their RPEs increased. RPE stands for rate of perceived exertion. So at 8 minutes, Summer continues to increase until 12 minutes, when she reaches 17 on the scale, and Max drops off completely with a steady decrease from 4 to 10 minutes. This may be due to fatigue or experimental method. Josh's results showed a steady increase over 4 values from 4 minutes to 20 minutes. He and Summer showed that they started to become more exerted as the test went on, whereas Max started to exert himself less halfway through the test and had a 37.5% decrease in his rate of perceived exertion. So moving on to blood lactate level. Blood lactate levels show different results for Max, Summer and Josh. We can see that Max's and Summer's lactate level rose as the test went on. Max's lactate level had a quick decline from 14 minutes to 20 minutes of 17.5 to 9.5. Summer's data also showed a decrease in blood lactate level from 10 minutes at 16.5 to 16 minutes at 13. Normative data says that your blood lactate levels during steady state exercise should increase steadily. This is shown by Max and Summer, but they both had a decline between 10 and 14 minutes. Josh's results can be disregarded, as this is due to experimental method, and when compared to the other data, it shows that it's not right. So I'm now moving on to my method. So before the testing starts, you need to take the resting heart rate. This is so that you can see the increase of heart rate when he starts to exercise. We will be recording the heart rate, blood pressure, O2 saturation, breathing rate, blood lactate and the Borg rating. These will be taken regularly, but at different time intervals. For example, heart rate will be recorded every 2 minutes, while the Borg rating will be taken every 4 minutes. Before the participant starts to exercise, we need to take their heart rate, blood pressure, O2 saturation, and breathing rate. We then got the participant to warm up for 4 minutes before the testing started, so the participant is comfortable and ready to exercise for an extended period. Once the testing starts, the participant is aiming to reach 60 to 70% of their maximum heart rate. Once the testing starts, the heart rate and breathing rate were taken every 2 minutes, while O2 saturation was taken every 4 minutes, and the blood lactate and board rating were taken every 6 minutes. Finally, all the tests will be carried out at post 2 minutes after the exercise to see what has changed and how quickly it has changed after exercise has stopped. The participant will also have to keep pedaling slightly to remove lactic acid from the muscles and cool down. So I'm now moving on to my 3 hypotheses that I did on the cardiovascular system, energy systems, and the respiratory system. So the first one was the heart rate hypothesis. So to measure the heart rate, we used a blood pressure monitor and oximeter before the testing began. Before the testing began, our hypothesis was that the heart rate would go for an initial anticipatory rise and then a significant rise in heart rate as our participant starts to reach their aimed working field. The aimed percentage of heart rate for the participant to reach was 60 to 80% of their maximum heart rate. We hypothesized that once this level of work was reached, their heart rate would plateau and become steady as a participant's body started to become accustomed to the level of oxygen needed by the muscles. Therefore, heart rate becomes steady as it does not need to rise to supply more oxygen to the blood. Then finally, we predicted that the participant's heart rate would drop quickly after stopping exercise. This is because the participant will be predicted to be working at a level which requires aerobic respiration. This means that there will not be an oxygen debt as the body has been constantly supplied with oxygen throughout the test as the participant has been working at a steady state. To get the results, we used a blood pressure monitor and recorded the participant's results pre-exercise and every 2 minutes, also post 2 minutes exercise. Normative data suggests that the same trends occur as the hypothesis that we predicted for the participants. It stated that there would be an increase of 60 to 80% in heart rate and a plateau when the body is accustomed to the oxygen demands of the muscles. It also shows a decrease in heart rate quickly after exercise stops. So moving on to my energy systems. For the participants, we hypothesized that they would be using the aerobic energy system. This is because the time frame at which the participant is working is far too long for any other energy system to sustain the work rate at the same amount of time. We recorded their lactate levels every 6 minutes and recorded his O2 saturation every 4 minutes. When compared to the normative data, we saw that the trends was a plateau in blood lactate levels and O2 saturation levels. During the test, we saw that the 66% of the participants followed these trends of O2 saturation and blood lactate levels, whereas the other 33% were found to not follow these trends of normative data. This may be due to experimental method where the equipment was not working properly. This means that this data can be disregarded as it may be an anomaly. So on to my final hypothesis, the breathing rate for the respiratory system. We hypothesized that the breathing rate would increase once exercise has started. This is because there is a demand for oxygen in the muscles because they need to respire in order to create energy. This means that as the demand for oxygen increases, the breathing rate in turn also rises since oxygen is taken in while breathing in order to saturate the blood. Once the participant reaches their required exertion level, the breathing rate will plateau as the body is accustomed to the amount of energy needed to supply the muscles. Once exercise has stopped, breathing rate will return to normal relatively fast as there is no oxygen debt around the muscles. So normative data suggests that there will be an increase in breathing rate at the start of exercise and then a plateau when the participant has reached their threshold and their bodies have become more accustomed to the work rate. It also states that there will be a quick decrease back to normal breathing rate after the exercise is finished. This is because there is no oxygen debt as the participants were using aerobic respiration throughout the testing. All 3 participants had different breathing rates at the start of testing. They all saw a plateau during exercise. This shows that they followed the normative data trends. There was an anomaly due to experimental method as Josh's results show there was a decrease and then an increase before his breathing rate plateaued. This is due to a warm-up beforehand, which raised his breathing rate, and a stoppage where the participant had equipment used on him. And this meant that when he had a warm-up, his breathing rate was already increased, even though the testing had not begun yet. So And then also when he stopped to have equipment put on him, it was also that showed also a decrease. So his results were slightly inaccurate.